Physics 1101, Exam 1 review. All right, first of all, the exam will be open from September 12th at 3 p.m. or so to September 16th at 8 p.m. All right, there will be no class on the 14th as a result of having the exam at that point, so I'll have class on Thursday. Okay, anyway, so exam will be about 25 multiple choice questions plus 5 or 6 short answer problems, short problems that you'll be writing in. All right, you get 1 attempt. It'll be timed. I think the time is about 80 minutes for the test. So you want it, and then I'll update the scores after the exam is closed. Okay? So, actually, all right. Actually, this is going to be 8 a.m. I forgot because that's when class starts. So it'll close at 8 a.m. on September 16th, which is the Thursday. So it'll close right when I start class review for the second part. So it will close at 8 a.m. I'll change that, right? So what is it going to be on? All right. On chapter 1, not a whole lot there. To this, what you'll have for chapter 1, just section 1.4, measurement, right, and uncertainty. So given a number, say 3.50500. All right, how many significant figures are in this number? Okay, if this is in meters, right? Or if I have number 0.00032, how many significant figures are in that? And if I have, say, multiplication or addition, say 5.43 plus 6.21113 meters. All right, what would the answer in that be in significant figures? I've gone through this already, talking about significant figures, realizing anytime you combine measurements, the answer is going to be number of significant digits is going to be the one with the least number of significant figures. All right, so that's it there as far as that's concerned. Scientific notation, so if you want to get it correct, so if I have number 3456000, that would be equal to 3.456 times 10 to the 6th. All right, you wouldn't include the zeros. If you did, it would be, again, 0, then would be, you would have 300 times 10 to the 6th. So the number of digits when you write scientific notation is the number, is how many significant figures you have. So in this case, it would be 7. So that's one way. If you write it as scientific notation, you'll be able to read it right away as far as that's concerned. The only other thing, as far as chapter 1 is concerned, are just the standard units, and then the units we've used. So units, that's section 1. So this is section 1.4. Section 1.5 will be just the different units. Prefixes, so giga, mega, kilo, all right, centa, So centimeter, millimeter, micro, so gigameter, micrometer, kilometer. So this would be like prefixes for, so this is the prefix. Micron, you actually don't normally use that, just write it as M. Or you could write UM. And then nano. So again, this would be the prefix, the Greek language. So these are the standard ones we'll be using for this semester. All right? So we don't normally go bigger than that. We don't normally go smaller than that. And then, again, keep track of units on a problem. So we have something like, say, acceleration is 5 meters per second squared. It's not, velocity is 5 meters, say 5 meters per second. So when you have a problem, make sure the answer, if I ask for an answer, is what is the velocity, what's acceleration. Make sure you include the correct units. If you're doing this text thing, you can do it this way. 10 to the second, that works. Where that sign represents 10 to the second. So it would be divided by, and so that's one way you could do it that way. All right, so this would be like 10, like so. So writing as just normal text writing. All right, so that's basically all chapter 1 is concerned. All right. Chapter 2 will be just on, and I've gone through all this before. Chapter 2 is on number 2, kinetic motion in 1 dimension. So again, average velocity, velocity average, change of distance over change of time, period. So whatever units it is, so how long it takes. So you go down to Minneapolis. Even if you stop, this would be what time you start, what time you get there. Say 4 hours it takes you to get there, including stops, divided by, well, you would take the distance divided by 4 hours. So that's the average. And then an instantaneous velocity, which is instantaneous. All right, is just the speed at a given moment, like for a speedometer. And it's also the slope of a velocity distance time graph. So the slope at any given moment, if it changes, is the velocity. So the slope is the velocity. So as it changes, so if it's constant, right, then the slope is constant all the way. As far as that, so that's instantaneous. So while we're still on this, we're talking about that. We might as well go into acceleration, which is section 2.4, which is divided by change of velocity over change of time. Right? And you have instantaneous acceleration. So we have the slope of velocity time graph. The slope is the acceleration. Here the slope is the velocity. So velocity time graph, again, if it's constant, velocity time, the slope would be constant here. So those are kind of graphs there, and look at that again. So is this is this a tangential line? This actually comes from calculus, but that's the extent of what we're going to be doing for this exam. Okay, and then problems related to that. Okay. Moving on. All right, so section 2.5, constant acceleration. have there are the equations I already wrote. So for x is x naught plus, v is v naught plus at in the y direction. So this is x, y, v in the y direction, v naught plus gt, where again, when we have the y direction, so g is minus 9.8 meters per second squared. Our second equation is x naught plus v naught t plus 1/2 at squared. And in the y direction, the only thing different is y naught plus v naught t plus 1/2 gt squared, as we've had before. And then the last equation is v squared is v naught squared plus 2a times the change in x. And if it says y is v squared is v naught squared plus 2g change in y, right? Now these are separate, but these be only if we're only dealing with the x direction, depending on what the acceleration is or calculating it. In the y direction, we're only having, the only acceleration will be due to gravity. All right, and then I had problems related to that. So we talk about free fall, throwing something up, or we have something accelerating linearly, horizontally. So those are the problems there related to that, and some of the examples I did with that. All right. And I went, particularly on chapter 2, I went through examples of that. This last thing is slope. It has to do with, I'll just clear up. The last thing is slope of line. It is from the last section, which if you want to get complicated about it, is such, but that is how you find, just if you want to get now fancy about it, that's how you do it. So that's chapter 2 is concerned. And the final part of the test, all right, is on just section 3.5, projectile motion. And that is section 3.5 and 6. And this is also talked about in lab 2. So make sure you get that done before, because lab 2 will close right when the exam opens on Sunday night. And for this part, projectile motion, we're just going to be dealing with the cases I went through of where we have, we shoot something horizontally with some speed, and it falls a distance y and travels horizontally distance x. So based on that, we can calculate, as I talked about in the chapter 3a lecture, how fast, how far out will it go, or how long will it take. Generally, how far it falls, given the speed, how far out it goes. So this is a projectile, again, launched horizontally as far as that's concerned. The only other part, section 3.6, if we have something which is launched, and this is also in lab 2, the other part of the basketball motion we'll get into more later in here. But in this case, what is launched, so what you'll see here, when it's this way, go x, and this is y, the graph of position versus time in the x direction will be just that sort of thing, because it's going horizontally at a constant, so it's some velocity you shoot it at. In the y direction, it's going to be a parabola, like so. So here in the x direction, velocity versus time, you'll see it be constant. And here, for y, velocity, this will be more like that. All right, and you can see that when you do lab 2, you'll see that this is what the graphs will look like. So for only what we're going to be doing here is we launch it, it goes a distance r, what we call a range. It's launched at some angle from the horizontal theta, so the range is given by, make sure I get that right, v naught squared times the sine of 2 theta over g, right? So g is gravity, so it's this number. Range is the distance that it travels horizontally. So it launched, lands at the same height. So this follows a parabola. All right, so that's basically all of the first exam. All right, the rest of chapter 3, including vectors, will be in exam 2. So that's it for there. Don't forget, it opens at, check the time when exam 1 opens. You get 1 attempt on it, and there you have it. So have a nice day. If you have any questions, email me. I'll be around on Sunday early afternoon if you have any questions.